Hello everyone and welcome back. In the two previous videos about nebulae, we discussed emission nebulae and reflection nebulae, focusing particularly on the physical mechanisms that determine their colors. I recommend checking out those two videos if you haven't already. In today's video, we will talk about the last type of nebulae, the most mysterious and least colorful ones, known as dark nebulae. We'd like to conclude this series on nebulae by discussing molecular clouds, which, as we'll see in this video, are closely related to dark nebulae and serve as the birthplaces of stars. Before we begin, I want to remind you that the best way to support me is by subscribing to the channel and liking the video. With that introduction out of the way, let's dive into dark nebulae. This type of nebula is mainly composed of hydrogen, but especially contains a large amount of dust. We've previously discussed interstellar dust in the last video, where we explored reflection nebulae together. For those who haven't seen it, here's a brief summary of the main characteristics of interstellar dust. It consists of tiny solid particles, grains ranging from millionths to hundredths of a millimeter in size. These grains are primarily composed of molecules made from elements like carbon, oxygen, silicon, and metals such as iron, magnesium, and sodium. The molecules making up the dust grains form on the cold surfaces of red giant stars. Cold meaning approximately 2,700–3,700 degrees Celsius, or they form from material ejected during supernova explosions. In dark nebulae, the density of interstellar dust is so high that it completely blocks light from sources behind the nebula. This creates regions that are entirely dark, hence the name dark nebulae. Dark nebulae can take on various shapes. For instance, they can have a highly extended filamentous structure, or a very high concentration of dust in an isolated region. In the latter case, these are known as Bok globules. Dark nebulae can have densities reaching up to 1,000,000 atoms per cc in the densest regions. The light from stars or other nebulae behind a dark nebula is absorbed by the dust grains within the nebula itself and thus does not reach us. However, the dust grains in dark nebulae, by absorbing starlight, become warm and consequently emit infrared light. This is why dark nebulae appear black to us in visible light, but appear bright in infrared. A dust-rich nebula near a luminous source, such as a star, may appear dark to us if it lies between the star and us, thereby blocking the star's light. If the dust is located behind or to the sides of the star, then we may receive light reflected by the dust towards us, and in that case, the nebula appears as a reflection nebula. A very famous example of a dark nebula is the Horsehead Nebula, visible in the constellation Orion. It stands out against the red background of the emission nebula IC 434. As the name suggests, the Horsehead Nebula, about 7 light-years wide, has a shape resembling the head of a horse. This shape is due to the strong turbulent motions of the interstellar gas in which it is immersed. It is believed that the nebula will be swept away in about 5 million years by the stellar wind from nearby stars. Dark nebulae are regions with very low temperatures, around 10–20 degrees above absolute zero, which is approximately 250 degrees Celsius. As mentioned at the beginning of the video, dark nebulae are not composed solely of dust but also of gas, particularly molecular hydrogen. Molecular hydrogen is a very simple molecule composed of 2 hydrogen atoms bound together. The presence of molecular hydrogen is closely linked to the presence of interstellar dust. Indeed, it is thought that dust aids in the formation of this molecule from hydrogen atoms. This is a crucial concept to emphasize. In regions where dark nebulae are observed, molecular hydrogen is typically present. This molecular hydrogen forms actual clouds called molecular clouds. Unfortunately, molecular clouds do not emit light of any color and are therefore not directly visible. However, there are techniques that allow us to study them. Before we continue, let's take stock. Dark nebulae are dust-rich clouds, shielded from external radiation, where molecular hydrogen forms clouds called molecular clouds. These molecular clouds cool down, becoming denser and more beautiful, thanks to their low temperature and high density. When something external disturbs a molecular cloud, the cloud begins to collapse under its own weight due to gravity. This collapse affects not only hydrogen but also the dust of the dark nebula in which the molecular cloud is immersed. When the gas pressure, which by that time has collapsed, has been compressed and heated sufficiently, the collapse stops. At that point, at the center of the molecular cloud, a sphere of hot and dense gas called a protostar has formed. Protostars gradually clear away the nebulae in which they have formed. It's fascinating how within cold and dark nebulae, rich in molecular hydrogen, hot and luminous stars that we all know are formed. We wanted to tell you that we will definitely make several videos about the star formation process, so be sure to subscribe to the channel. There are giant molecular clouds hundreds of light years across and with a mass about 100,000 times that of the Sun. These particular giant molecular clouds are called giant molecular clouds. In correspondence with these molecular clouds, as you may have understood, we find large dark nebulae, so a large amount of dust, but above all, high activity of star and star cluster formation. An example of a giant molecular cloud is the Orion Molecular Cloud Complex. This complex is a vast region of star formation located about 1,000 light-years from Earth and spanning more than hundreds of light-years. It is so large that it stretches across the entire constellation of Orion. As you can see, molecular clouds are not only characterized by the large presence of dust in the form of dark nebulae, but also by the presence of typically blue reflection nebulae and red emission nebulae, i.e., the H regions, which are the last two types of nebulae we discussed in the two previous videos. These regions form in the molecular cloud regions where new stars have just ignited. Indeed, as we have seen in the previous videos, the color of reflection nebulae is due to dust grains reflecting the light of nearby newly born stars, while the red light of H regions is due to hydrogen atoms that, after being hit by the ultraviolet light of young stars, ionize, i.e., lose their single electron. When these electrons return to being bound to hydrogen nuclei, they emit the typical red light of these nebulae. The Orion Molecular Cloud Complex not only includes the Horsehead Nebula but also the famous Orion Nebula, visible to the naked eye even from the city as a small fuzzy dot. It is a diffuse nebula, i.e., an extended nebula with undefined boundaries, where the various colors of this molecular cloud are due to the presence of various H regions, reflection nebulae, and dark nebulae. Approximately 700 new stars are forming in this nebula today. It is the light and stellar wind from these stars at the center of the nebula that has pushed away part of the nebula, creating a cavity within it. In fact, the light from the stars has carved out the nebula itself, which is why we can see the innermost parts of the cloud. It is believed that at this rate, within about 100,000 years, most of the nebula will be swept away. Another example of a molecular cloud and thus a star-forming region is found within the large Carina Nebula, where there are large clusters of dust and the stellar wind from newly formed stars that shape these dark nebulae. Or what about the famous Pillars of Creation, a dark nebula with a very particular shape, where new stars are forming and whose stellar wind is slowly shaping and will eventually disperse the pillars themselves. The Pillars of Creation, rich in molecular hydrogen, are found within the Eagle Nebula. This nebula, as can be seen from the typically red color, is a large H region. The entire region is a star-forming region. Another example of a giant molecular cloud is the Taurus molecular cloud. This, unlike the Orion molecular complex, does not feature any emission or reflection nebulae. This is because there are no bright, hot, young stars within this cloud that ionize the nebula gas or whose light is reflected by dust grains. Consequently, this cloud only features typical dark nebulae associated with molecular hydrogen clouds. Not having bright stars does not mean that stars are not forming within this cloud. On the contrary, within the dark nebulae of the Taurus cloud, molecular hydrogen is collapsing, forming many protostars. It's just that the visible light from these protostars is heavily blocked by dust. But how do we know that protostars are actually forming within the dark nebulae of the Taurus cloud? Well, just look at this molecular cloud in infrared. Within the dark nebulae of the Taurus cloud, you can see very bright spots. The light from those spots is precisely the infrared light emitted by some forming stars, light that has managed to penetrate the thick layer of dust and reach us. Speaking of the Taurus cloud, several scientific papers have reported a very interesting finding. Based on recent observations in radio waves, traces of polycyclic aromatic hydrocarbons have been found for the first time in the interstellar medium. In particular, they were found in the Taurus cloud. These special organic molecules, based on carbon, are characterized by ring structures and are very interesting because, through certain chemical reactions, they can form RNA molecules, ribonucleic acid, which is a large molecule similar to DNA. In fact, it is believed that the first forms of life on Earth were based on RNA rather than DNA. In summary, organic molecules have been found in interstellar space that could, under appropriate conditions, form genetic material, i.e., the building blocks of potential life. I wanted to conclude this series of videos on nebulae by saying that there are different types of nebulae that can be seen through visible light, but in reality, there are entire regions of the interstellar medium visible only through radio waves or where the light is emitted through other physical processes. We hope we've been clear and provided a comprehensive overview of the different types of nebulae and the physical mechanisms underlying their magnificent colors. Let us know in the comments if you also love these magnificent celestial objects and if you have a favorite. Finally, if you enjoyed the video, leave a like and share it with as many people as possible. Thank you for your attention, and we'll see you in the next video.